So, problem 1 from our section 5.5. So here's our question. It says the population of Stewart can be modeled by this function, where t is the number of years since 2020. Use the function above to answer the following questions. What was the population of Stewart in 2020? So in this problem, it is for t is the number of years since 2020. If they are asking us what is the population of Stewart in 2020, then that means t is 0 because of how it's defined originally. So if t is 0, it makes multiplying times this 0, and you get e to the 0. Well, e to the 0 is 1, and so our answer is 16804. Our next question under this one, in what year is the population of Stewart projected to be 22,685? Right, and so we will put that in for P. And your first step is to divide this out so that you have this E by itself. And so we're going to divide on both sides by 16,804. And you have two different things you could do here. Your next step is going to be to take the logarithm, natural log of this side on the right. So you'll do natural log of both sides to bring this exponent down, and then you'll divide by it. If you go ahead and take the natural log of this fraction, you need to keep all those digits. So an alternative to that is to not actually take the log yet, but just to write it and do it in one shot and let your calculator hold it. So not really doing it yet. And on the right-hand side, that brings your exponent down. Whoops. And the ln of e equals 1, so that doesn't really matter. All right, so we have this logarithm equal to this. We want to isolate t. So we're going to divide by this piece. So if we waited to do this in our calculator, now we can divide by 0.001858, and that kept us from entering all those digits so many times. And it keeps us from the round off error. So we'll try it that way. Let's pull up our calculator. And so we'll do natural log of 22,685 divided by 16,804. close parentheses, go ahead and do divided by 0.001858. Enter. So we have 161.5, and the question says, in what year, and round to the nearest whole. So we're going to push up with this. So we'll have 162 years. Add that to 2020. So this is 2182, in the year 2182. And there we go. So that is just one way to keep from having to write so many digits here. If you put this in early, if you divided this early and then took the log, you just have to rewrite and keep all the digits. Right, so let's look at question 2. And so here we're going to look at Port St. Lucie's population. And so here is our model, which is standard. They have just switched the variables from a and a sub 0 to y and y sub 0. Doesn't matter, y sub 0 or a sub 0 will always be your initial one. All right, so the 2010 census found the population was this. The 2020 found the population was this. Use the exponential growth model, where t is the number of years after 2010, to write an exponential growth function for the city of Port St. Lucie. So what we're going to have to find here is the k using these so that we'll have a general formula. So first we will use these two. So we're going to use the 195,034, and our initial in 2010 was 164351. E. We don't know K, that's what we're going to find. And between these 2 years, 2010 and 2020, subtract those and you get 10 for T. Right, and so we want to solve for K, and we will divide this out and then take the logarithm. So we're going to divide 164,351. And again, because we know our next step is take the logarithm, I think we'll wait and not actually divide it out so we don't have to write so many numbers. All right, and so now I'm going to take the logarithm of both sides. And so your 10K is going to come down. ln of e is 1, so that's off. And so we can go ahead here and divide by 10. So I'm taking a little tiny shortcut there. And that will get us K. So we'll do this in one shot in our calculator. So natural log 195,034 divided by 164,351. Close the parentheses. And now go ahead and do divided by 10. Enter. And so we are getting 0.01711. I'm going to put down a bunch of digits. 695. All right, we have something new here to deal with that we haven't had before, and it says round the growth constant k to 4 significant figures. So that idea is new. And for significant figures, you don't count any of the zeros at the front. So you start with the first non-zero digit. So we have 1, 2, 3, 4. So a 6 would push us up. So this is going to go to a 2. So we're going to use 0.01712 would be to 4 significant figures. All right, so now they want us to give the growth function. And so we will have y. So we could do it at any time. And we'll put our original amount, 164351, e to the 0.01712, and we'll have t there. So this should be our growth function that goes here. And we'll check. So we're good. I was a little slack here and didn't put the 0 on the left of the decimal. It should be okay without it mathematically, but if you want to be exact, put it in. All right. Now they ask us to use this population growth model to predict the population of Port St. Lucie in the year 2036. Right, the original model was 2010. So we're going to find t right here. So t will be 26 years. And we will just have to plug in to do the math on this. So we'll have y equals 164351 e to the 0.01712 times 26. So we're not taking a logarithm here, we're just going to do this math. So when we enter in our calculator, we'll start with the e and do this multiplication last. So we're going to do second e to the power. We'll use parentheses. So 0.01712 times 26, close parentheses, and you could hit enter there if you want, right? That number times, now we'll do it times the 16,431.51. And so we get 256498.9, and this probably said to the nearest whole number, so this 9 would push us up. So 256499. So we're good there. And then they're going to have us do one more question. We're going to use this model, and they want to know when the population of Port St. Lucie will be this. So we don't know t. This time we'll have to do a logarithm of both sides. So we're going to go back to this. Sorry. All right, so our y is going to be the 28,7053. Our initial is the same, because that's what the model was based on. E to the 0.01712 t. So now we'll want to solve for t. The first thing we have to do is divide out this initial. But we'll wait to divide it on the left. We'll just write the step. And then we'll take the logarithm of both sides to get the exponent to come down. So we're going to take the logarithm of this. Oops, I left off the E. And that will bring this piece down. So 0.01712 t will equal this. And so then we'll divide by this coefficient. And that will leave us t. So this is what's going in the calculator. So we'll take a natural log, 287,053 divided by 164,351. Close your parentheses. And we'll go ahead and divide by 0.01712. Enter. And we get 32.57. And they would want it in the nearest whole number. So we're going to go with 33. So 5 would push us up. We're going to add that to 2010 because that was our original. And so we should get 2043. And we did. That's a good sign on these word problems. All right, problem number 3. So this is something that biologists would be interested in. And this is just an application in that field. And so we're looking at bacteria growth here because this is a growth model that we have. And so E. coli is essential for modern biotechnology research. One reason for this is the ease and speed at which E. coli can be cultivated in a laboratory. Under ideal laboratory conditions, when this bacterium is grown in a nutrient broth medium, the number of cells in a culture doubles approximately every 24 minutes. Suppose an initial colony of 100 E. coli bacteria are used for an experiment. Use this growth model, where T is measured in minutes, to write an exponential growth model for the bacteria colony. And so we're going to have to find K. And initially we're having 100. And we're going to use the fact that it says it doubles in 24 minutes to help us get to the K. So we don't know the growth constant. All right, and so if this doubles, this would be 200, or we could just divide those out and have a 2 here. That's where we're going to go. So we have E, we don't know K, and this happens in 24 minutes. So next step would be divide out the 100, and it would have been perfectly fine just to have put a 2 there to begin with. We'll divide that since it works out nice. And then we'll take the natural log of both sides to get our exponent down. So we're going to have the ln of 2 equals the ln of e to the 24k, which makes this come down. This is 1. So I didn't punch ln of 2 in yet. I'm going to wait and do the division with it in the same step. So now we will divide out the 24 to get the k. So natural log of 2, close, divided by 24, enter. So we get 0.0288881. And we'll go ahead and go with the 4 significant figures. I think that is actually what they said. Yes, find the k to the 4 significant figures. So you don't count the 0, so 1, 2, 3, 4. When you look to the right, the 1 is not going to count. So we will use 0.02888 for k. And now we want to write the model. So y will equal our y sub 0, the initial one this is based on is 100 e to the 0.02888 t. So this should be our first answer for the growth function. So we're good there. And it's okay that they switch to minutes here. Just make sure that that's what you plug in is minutes. So the next question, approximately how many bacteria will be present in the colony after 180 minutes? So if they switched here and said 3 hours, you would have to go back to minutes with it. So just that's something to watch. So whatever time frame you start with, you need to stay in that time unit. All right, so we're going to look for y. So this first, or our second question here is just going to be to plug in. And this will be 180. So we're ready to go to the calculator. Clear. And we'll start with the e and do this multiplication last. So we'll do second e to the power, and you want parentheses because you have math inside. So 0.02888 times 180, close, and then we're going to do times 100. We could hit enter here, or we could go ahead and do times 100. It doesn't matter. Because you wouldn't have to write it down either way. You would still have it sitting there. So this would be 18098.2 and round to the nearest whole number. So this will drop off. So 18098. Very good. And this next one, they want us to find t this time. How long will it take the colony to reach? And I believe this is 10 billion. So I have to be real careful here with the zeros. Let me get down just enough till I can still see the formula or the model. Okay, so on this side we're going to have 1 0, comma, and 9 more zeros. Equals 100 e the 0.02888, and we're going to solve for t. So first step will be to divide out 100. It's fine to go ahead and do that because it is going to be, it's going to work out even. You're not going to have a decimal remainder. It's going to take 2 zeros off of there when you divide by 100. So now instead of 10 zeros, I'm going to have 8 zeros. And then I'll be ready to take the logarithm of both sides. And this is where I would wait and not actually do it yet. Makes this come down. ln of e is 1, so it doesn't matter. And to go ahead and solve, we're going to divide by this piece. So I'm going to just take a shortcut and go ahead and do that division. 0.02888. And that will give me t. So now I'll go to the calculator. And we have natural log. And I have a 1 with 8 zeros. Close. Divided by 0.02888. Enter. So 637.8. And this 8 would push us up. So 638. And we are in minutes. So just go and check. And there we're good. Any question there? Right. Number 4, I kept having trouble with it before. Round off error. So, and I went with the standard thing of going to 4 significant digits for K. I'm going to try that and enter whatever we get. And if it marks us wrong, we'll backtrack. But it did not give me the same answer. But it doesn't say in it to go to 4 significant figures. So that could have been D issue. It does have a piece, though, that I wanted you to see. So we'll go ahead and do it, even though I may get in trouble with it. All right. The doubling period of a bacteria population is 43 minutes. After 69 minutes, the population has grown to this. Determine the initial population. All right, so we're going to find K with this first piece. So we have Y equals Y sub 0 e to the kt. And we don't know Y sub 0 or Y, but we know that it doubles. So whatever this is, this will be twice as much. So we can go ahead and do the division. So Y divided by Y sub 0 equals 2. That is the doubling piece. And so that gets us to e to the k, and our t for that is 43 minutes. So we do this to find the k. So we'll take the log of both sides. So log of 2 equals log over here, e to the 43k. This will come down. So we have 43k equals, ln of e doesn't matter, ln of 2. And now we'll divide by 43. So we'll get k. And we'll push this in to our calculator. So natural log of 2 divided by 43, enter, went 0.161197. Right, and if we go to 4 significant figures, this would be 1, 2, 3. The 9 would push us up to a 2 here, which to me that should be appropriate. So we will put our model in. Oh, they don't want our model. Okay, so our model is y equals y sub 0 e to the 0.01612 t. Right, and then we're going to use the second part up here. So after 69 minutes, the bacteria's population has grown to this. So we have 21716 equals, we don't know this one, e to the 0.01612. And this is a 69. All right, and so we don't have to take a logarithm this time because we don't have a variable in the exponent position. So what we need to do, though, is to isolate this. And so we can go ahead and just divide by this whole piece. So I'm going to leave it like that. And keep from getting any more round off. And then we'll go to the calculator. So I have 21716. And I'm ready to just go ahead with a division. I'm going to put this whole denominator in parentheses just because I'm cautious. All right, parentheses are your friend. So second e, right? We're going to a power, and we're going to put that in parentheses. So 0.01612 times 69, close. That is for your math that was in your exponent position. And then I'm going to close again for this first one and hit enter. So I am getting 7140.4, and they want us to go to the nearest whole number, and this is the same thing that happened to me earlier, which would be 7140, and I believe their answer was 7141, right? I'm going to enter 7140 and see if it will take it. And I'm going to go ahead and submit that. It did take it. Okay. So it's fine what we did because we were going with a standard practice. I did not check that by actually putting it in earlier, but I was unhappy that it gave me the wrong thing. All right. Let's go to the next piece. And so we're going to determine the population of the bacteria colony after 4 hours. This is where you have to watch out because they're switching the time unit. Right? We started in minutes. That's what the model is for. So switch this 4 hours to minutes. And let me scroll just enough so I can still see that formula. All right. So we're going to determine the population. Our initial is what we just found, the 7140 in the step above. And I should not have switched to a Y, to an A there. So Y. This is our Y sub 0 that we just found. E to the 0.01612 and 4 hours. So 60 minutes in an hour. This will be 240. And this one is not going to require a logarithm because you're not solving for a variable in the exponent position. So we are just going to punch it in and do the math. Start with your E. So second and E to the parentheses 0.01612 times 240 close. And I can go ahead and do times 7140. If you wanted to hit enter, that would have been fine. And then times the 7140. So I am getting 3,4,1,8,9,8. This will drop off to the nearest whole. And that is a little different than I am here. A few more digits, but let's try to enter that and see if we're okay. So I should have another try. So 3, 4, 1, 8, 9, 8. All right, so it accepted it. It does allow for some round-off error in the answers, but I'm not sure. They must have used all the digits for the K originally to have had the difference there. Right. There was one that gives us scientific notation. Yes. Problem 5. So this one, we get something that's in scientific notation, and we have to take it out of that. So we need to do that one. And this is our first problem with something decaying. Okay? And we have to work with the idea of half-life. Half-life is the amount of time that it takes for half of a substance to decay. All right, so we're working with Marie Curie. She was a Polish and naturalized French physicist and chemist who conducted pioneering research on radioactivity. She was the first woman to win a Nobel Prize, the first person and the only woman to win the Nobel Prize twice, and the only person to win the Nobel Prize in 2 different scientific fields. She was part of the Curie family, a legacy of 5 Nobel Prizes. She was also the first woman to become a professor at the University of Paris, and in 1995 became the first woman to be entombed on her own merits in the Pantheon in Paris. So all that is just to kind of give you the info that goes with it. There was nothing in that we needed for the problem. So it says she died in 1934 from aplastic anemia, a rare condition linked to high levels of exposure to radioactive elements like polonium and radium. Due to her many years of exposure to these radioactive elements, her remains are dangerously radioactive and entombed in a lead-lined coffin in France's Pantheon. The thick lead shields visitors from the dangerous radiation that still emanates from the contaminated remains. Right, so down here is the problem. One of the isotopes Madame Curie studied was radium-226. Right, this 226 is not a number that's going to have anything to do with your problem. That's part of the isotope name. Right, it has a half-life of 1600 years, so we're going to need that part. So that is how long it will take for half of the substance to disappear. Right. Determine how many years are required for the amount of this radium on the remains to reduce to this. So the first thing we have to find is the K. So from our model, y equals y sub 0 e to the k t. And we're going to use this half-life that they've told us, right? So y divided by y sub 0 is going to be 0.5. 50% will remain. So 0.5 equals E. K is what we're looking for, and they've given us T, 1600. So we're going to take the natural log of both sides because we want to solve for an exponent. The natural log makes it come down. So we're going to do natural log, and we'll do natural log over here, of 0.5 and this will come down. ln of E is 1. So I'm waiting to figure out this natural log of 0.5. If you punch it in, you're going to get a negative. Don't be surprised by that, because if something is decaying, it is going to have a negative growth value. Right, so we'll go ahead and divide by our 1600. To get us to K. This will go in our calculator. So we're going to do natural log of 0.5 divided by 1600. Enter. So I didn't leave enough space. Negative 4.33216. I'm putting a bunch of digits because we have to take this out of scientific notation. E to the negative 4 means that it is times 10 to the negative 4. Right. So we want to get this out of scientific notation. We'll apply this math, and it means your decimal is going to go 4 places to the left. This will be 1, so we're going to need 3 zeros. And then this will be far enough. 4332, because the 1 can drop off, will give us 4 significant figures. All right, and I'm a little slack about this 0 in front of the decimal. You can get away with it mathematically. If you're in some science classes, be very careful, because some of them are very picky about actually putting it on there. All right, so this is our K. Now we'll go back to our problem. All right, and so determine how many years are required for the amount of this on the remains of Madame Curie to reduce to 4.7% of the amount of the original. So we are not going to know the original here, but instead of the 0.5, we are going to switch this out of 4.7% over to a decimal, just like we did the 0.5. 50% is 0.5. So 4.7% will be 0.047. This is our A divided by, sorry, not A, we're using Y's here. It's our Y divided by Y sub 0, which we weren't given either one of those. So we have 0.047 equals E to the negative 0.004332, and we are looking for the time. This one will take a logarithm to make it come down. So we're going to do the logarithm of 0.047 equals your logarithm of e to the negative 0.000433 That will make this come down. Your ln of e equals 1, so you can throw it away. And I'm going to go ahead here and divide by this. And that will give us t. So we're ready for the calculator. So natural log 0.047, close your parentheses, divided by negative 0.000433. 3, 3, 2. And so we get 7058.1 and round to the nearest whole. So 7058 years. There we go. And I had a little different answer when I put that in before. I must have rounded more. I probably punched this in first. It's better to punch it in the way I've been showing you in this video, to wait as long as you can and not have to write anything down. We'll have a look at one more problem. Problem number 8. So, says caffeine has a half-life of 3 hours. So 3 hours for 50% of it to be left. So for half of it to disappear. An average 8-ounce cup of coffee contains 105 milligrams of caffeine. Suppose you consume an average 8-ounce cup of coffee. Use the exponential decay model, which is here, where t is measured in hours, so that's where we started, to write an exponential decay for the amount of in milligrams of caffeine in your body. So what we're going to find first is the k. So we have y equals y sub 0 e to the k t. Now, this y that's left divided by our initial amount is 50%, is what's left. So we need to divide that out and have 0.5. So y divided by y sub 0 equals 0.5. K we're going to find, and they told us the half-life, which is where we get this 50%, is 3 hours. So we're using 3 for our t, and we're going to solve for k. So we're going to solve for an exponent. That means we need to take a logarithm of both sides. So we're going to take natural log on both sides of 0.5 equals natural log of e to the 3k. This will make our exponent come down. And ln of e you don't care about because that is 1. And we want to solve for k, so we're going to divide by 3 here. Then we will go to our calculator. So we have natural log of 0.5. Make sure your parentheses closes there. Divided by 3. Enter. So we have negative, and we expect negative because it is decaying. So our caffeine is disappearing. And they ask us to go to 4 significant figures, I believe. This one did not start with a 0, so we're going to be okay here. The 4 would not push us up, so we'll use negative 0.2310 for our k. And now they want us to write our model. So y will equal our initial, which is 105, because that's what the model's based on, so it needs to be in there, e to the negative 0.2310 t. Because here you can put different t's. And it is not giving me a key, because I worked this once before. So I am going to type it in. right, and we'll scroll so I can get back to the function. We mislearned patience, huh? All right. After 15 hours, how many milligrams of caffeine will be left in your body? So we're going to work with this and just plug the 15 in for the T. So we're ready for the calculator. No logarithm here because you are not solving for an exponent. Clear? Start with your E. So second E to the power. Use parentheses. Negative 0.2310 times 15. Close parentheses. Right? You could hit enter there if you want. But you've closed your parentheses on your exponent, so you could also go ahead and do times 105. If you have the TI-84, you have to come down out of the exponent position. But I think you would know that at this point. So 3.28. And they say round the solution to 1 decimal place. So 3.3 would be to 1 decimal place. And this is milligrams. Right. Assuming, so this was our second answer. So this was our first answer. Our second answer. And third part of the question. Assuming no additional caffeine is consumed, how many hours will it take the amount of caffeine in your body to reduce to 1.7 milligrams? So this is what we want left, is the Y, so 1.7. Your initial is still 105. E to the negative 0.2310. We are looking for the T. So this time we will need to take a logarithm of both sides because we want to solve for something that's in the exponent position. I need to do something before I do that logarithm. You can't take that logarithm with this 105 on that side. So divide both sides by 105. So I'm going to just leave that for a moment, but then it will go in the calculator. All right, and now I'm going to take the logarithm of 1.7 divided by 105. Take the logarithm over here of e to the negative 0.2310t. That will bring my exponent down. Negative 0.2310t. ln of e, which is equal to 1, so it doesn't matter. Right, I'm going to take a little shortcut here, and I'm just going to go ahead and divide by this negative 0.2310 rather than rewriting that step. So I'm ready for my calculator. We'll clear. So I'm going to do natural log. It starts out my fraction, 1.7 divided by 105, close your parentheses, and then we'll do divided by negative 0.2310. Enter. So I have 17.849, and they want to go to the nearest whole number, so I didn't need all that. So 18 hours. So this would be to just get the caffeine down to that point. Very good. So those were